information. And the data of the healthcare administrative data of the public service are, for example, the drug prescription registry, outpatient registry, or hospital discharge registry, that are structured data but are administrative, so they lack of clinical information and outcome. So we need to use medical records to join information from the pathway of the patient to the outcome or clinical information. One way to achieve this is use natural language processing. Natural language processing describes a set of techniques used to convert written text into interpretable data set that can be analyzed by statistical and machine learning models. Natural language processes includes sentimental analysis, thematic analysis with unsupervised machine learning models, and predictive modeling with the supervised machine learning models. The application with healthcare are to understand the health concern of population from social media, to process large volume of medical records, or to quantify or qualify patient outcome and experience for their own words. The limitation of the methods is the needs of a large number when you have a large number of independent variable, and you need a big sample size, a large sample size. And when you have a small data set, the increase in the chance of model overfitting is high, and it's important to validate the supervised machine learning algorithms with the independent data that needs more data to do this process. Our group tried this type of technique to find a semantic annotation from clinical notes, and we extract data that are unstructured data to join with the information of the healthcare system to analyze the pathway of the patients. We use algorithms that join vocabulary and rules with artificial intelligence to extract some clinical records like BRCA, estrogen receptor, the presence of estrogen receptor, the stage of the tumor, and the breast cancer tumor, and so on. Another application of machine learning in the biomedical research is the automation of literature screening for systematic review. The systematic reviews are widely used in the evidence-based medicine. The evidence-based medicine is the base of the medicine today. Conducting systematic review for clinical decision making is time-consuming and labor-intensive, and with the big amount of the article that are increase every day, it's time is very difficult to update systematic review periodically. So there are many algorithms to do automatic literature screening, but in some cases we have a high sensitivity, as high as 95%, despite the expense of specificity. And automation system may have low specificity. It's also important to evaluate how much reviewing work the reviewers can save in the step of screening. So it's important to understand if using this type of technique that is good for extract information and publication, it's enough important to the reviewers, because they have to do a work afterwards. The last example of biomedical research in machine learning is the cause inference. Big data and high performance computing machine learning are increasingly becoming a key in precision medicine. But precision medicine not only predict risk and outcomes, but also by waging intervention. An interventional clinical prediction model requires the correct specification of cause and effects and the calculation of so-called counterfactual. From a clinical point of view, we have a randomized clinical trial that permit to test the cause hypothesis since randomization, and we don't need domain knowledge. But we every know that clinical trials are a small part of the data that we have. On the other hand, we have the observational studies that are commonly affected by confounding and selection bias, and without robust assumption, it's not, the cause inference is not feasible. But we have a lot of observational study that can help us to improve our knowledge. From a machine learning point of view, data-driven prediction models are often mistakenly used to draw cause effect, but neither parameters or non-prediction necessarily have a cause interpretation. And interpretation of input-output mechanism from unveils the cause-effect relation by a black box. It's difficult to understand, most of the clinician. But today we have new step forward for this. And when you join deep learning with target trial and model transportability that are cause tool to understand the cause effect, we can do a step forward. In conclusion, we can see that data are the new oil of today, and data allow us to take a step forward in biomedical research using this type of algorithm. And nowadays we have different solutions to tackle the issue for data retrieval and cause inference. Thank you for your attention, and I leave the word to the other speaker.
Thank you very much, Andrea, for your nice introduction. And there is a very nice question in the QA box below, but I think that it would be nice to address it in the floor discussion, because it's a question on sample size in a way, according to statistical learning and according to machine learning. So if you don't mind, I would keep this question for the floor discussion, and I will move on to the next speaker, Corrado Lanera. Well, it's a pleasure to introduce Corrado Lanera. Corrado received his PhD in Biostatistics at the University of Padova just a couple of years ago, and in collaboration with the University of Pennsylvania. And now he is assistant professor at our university, and he is a very talented data scientist, a proficient R user, programmer, developer, and he is also responsible for the lab of artificial intelligence in medical science. Corrado, you have the floor.
Okay. Thank you, Ileana, for the too much good words. Okay, let me share the screen. Okay, can you see them? Okay, perfect. So, okay, thank you for having introduced me. And what we're talking about today is machine learning assisted systematic reviews. So here is some contact detail for me, if you like. And we are going to talk about a slightly introduction to systematic review, and next we touch how machine learning works to understand what are the bricks of our topic, and next we we are going to see how systematic reviews can benefit from machine learning and automation in general. After that, I would like to show a simple case study we done and conclude with issues and challenges. So what is a systematic review? If we look at the scientific evidence pyramid, meta-analysis and systematic reviews are placed on the top of them because their aims is to collect all the evidence that all the other studies in the scientific community have provided and results that we have to gain an overview of all of that and more robust results. So what we have to do is think about the systematic reviewing process as a process itself, not only as a deliverable. It's not an object. It's a methodology. So as Professor Tipshirani said yesterday, the first and maybe the most important aspect is your question. So the first things you do and you have to start is to provide a specific question you want to address. Next, you start to look around some exploration of the scientific production to look for some answer of that. And given the preliminary answer, you can refine and create your search strings and what you want to include and what you want to exclude, and all of that have to be put in a rigorous protocol that should be published for others and for yourself. Only at this time, with a precise procedure to conduct a systematic review, you can start to have the practical searching, so the collecting of all the records you can find on the topic. And after that, on all the records you have retrieved, you should screen them to throw out what are not of interest accordingly to the inclusion and exclusion criteria that you have posed. And finally, you should extract the information, the relevant information for your questions, and summarize or synthesize or analyze them together to product your report. And after that, given that a systematic review and an analysis and meta-analysis are not a fixed point results, but are dynamically changing with the time. So with the more study come out, you should also have the needs and the possibility to update it, and so to restart with a new search and with the same criteria, with the same protocol, and to update your findings. So in those steps, the most resource consuming, because they are not only time but also people and money resources that are consumed during the process, can be mainly in three phases. The broad phases, the question one, in which you can possibly retrieve tens or hundreds of thousands of records, and the main questions here is how you can create a good search strings. So how can you compose the keywords of the search strings together, which keywords to select, and which sources you should investigate, and how can you translate your search string to different sources. And you have to consider even the problem that some relevant sources cannot admit a good translated search string. And after that, possibly you come out with many duplicates record, and so you have to identify them and to filter out the duplicates. After that come the possibly most expensive in time and effort phases of a systematic review, that is the screening phase, in which across your tens or hundreds of thousands of records that you have retrieved, mainly quite every one of them should be excluded, and you left out with mainly 10, 20, 50 records overall out of all of that amount. And so how you can think of strategies to save time in these exclusions. And finally, for the analysis of your final retrieved and retained records, you have to have some strategies you can have some strategies that automatically help you to retrieve information for that. But this is a topic we don't touch today. So among all of this process, you can keep track of your findings and of your exclusion for what you exclude and include, and you should follow the Prisma flow diagram, that is the preferred reporting item for systematic reviews and meta-analysis. And as you can see in the 2020 update, there come in a field in which automation is included. So it started to be actively considering in the creation of the flowgram. Just to make you an example, also this process can be quite complex to follow, and also for that process there are some tools online that can help you to create along the road to create your system to produce your systematic reviews, help you to produce your diagram. Okay, so how automation can save you time? So for the question part, you can think about strategies to save your time that are commonly used, as something like find and replace words, maybe with all uppercases to highlight something in the text that can help you to speed up the screening procedure, or can help to define a more extensive strategies, considering words that can be variation of the word or synonyms, or maybe wrong typed words in the text. And for the search strings also, you can translate it semi-automatically using maybe regular expression or something like that to convert your string from one engine to be used to other searching engines. And regarding the screening phase, clearly you can use and you have many record manager software that can find for you duplicates, and many of them can be based on MLT engine possibly. Or you can also try to use negative search for exclude records, something like, I don't know, to search for rats to exclude all animals or a great amount of animals studied that are not human study. Or also you can highlight words, etc. But this automation can help you in some way, but even all of them can be assisted, or can give more help you with machine learning techniques. So how machine learning works? In 1959, Arthur Samuel says that machine learning is when a computer gains the ability to learn without being explicitly programmed. This to me means two things. The first thing is that computers have learned even before machine learning, but in different ways, in a different way. And the second thing is the explicit way in which now the computer is learning, so without being explicitly programmed. So that means that before machine learning, computer are used to learn, but with the explicit program. What does it mean? So you can think of traditional programming or learning like when you put inside your machine both the input data and the algorithm. You can think as what happens in Neo in Matrix when he's inside the helicopter and say, I have to learn how to drive the helicopter, and the algorithm comes in his brain, and the output is that the helicopter is flying because of his training. And so you directly inject the algorithm in the machine, and you have the output at the end. While in the machine learning paradigm, you have a different approach. You have a training strategies, and you apply your training data using this strategy to learn. And what you are out is not a result. It's not the airplane is flying now, but is more like a superhero that in the movie are quickly training itself, and at the end the character is changed. It's not you don't have the effect of, it's not the effect, the topic is the changing in the machine, is the changing in the character. So at the end you have a learned algorithm that you can use with an input data, and you have you have an output. So how can you learn your algorithm? What are the main types of algorithm that can be, I think, of interest for us today? They are three mainly, and the first one is the unsupervised learning, in which you provide data that are not labeled. So you provide only the data as they are, and the learning strategies is to find similarities and correlation within those data. Think about a child that is exposed to the world and know anything. You don't have labels and don't understand the labels, and start to make some consideration of them and say, oh, okay, those are humans, those are objects, simply, and comes more complex. So it's only a matter of group things that are similar, and I like those similarities. Next to that, we have supervised learning that we can call passive learning, because we have two distinct phases. One in which we provide the algorithm with data and label, so with the results, and you create your algorithm, your trained algorithm. Something like when we study for an exam, we have exercise and solution. We train ourselves in exercise and solution, and next we test them, or we apply our new knowledge with new data and have a result. So based on those errors, because we know the solution, we know how many errors and where we made errors, we can improve our knowledge and our learning. At the end, in active learning, we suppose that we have an oracle that knows anything. And so the rule of the learning algorithm is to ask the oracle the correct answer based on what it retains it is the best question to do. So think about an interactive lesson between teacher and students, in which the student come out with a question, and based on the answer, put to the teacher the next question that is focused on his new knowledge that he gains. That can speed up that much the ability for the algorithm to train itself, because every stage, every cycle is more focused on what he considers the most effective ways to improve itself. Okay, so but how all of that things works? We focus now mainly only on a kind of learning that is called now deep learning and neural networks, as we also have seen yesterday. All of that is only a commercial ways of speaking, because everything of that can be simply viewed as the maybe generalized logistic regression that is some way boosted. And so in this way, we have simply our inputs. We consider some weights that they can be basically random numbers, and we provide a simple weighted sum of those weights and inputs, and apply them as an input to a nonlinear function, and that nonlinear function give our desired output. So within this building block, we can create a network of neurons that create our neural networks or our learning networks. And given that every neurons that comes between the input layers of neurons and the output layers of neurons, they are called hidden layer. And when you have more than one hidden layer, you are used to call that network as a deep learning strategy. As I said, you can consider quite every set of W's numbers. So here, those numbers, you can set them as you want. And for every set of those numbers, you can do your multiplication, you can do your sums, you can apply the result to the nonlinearity and have a result. So for every possible set of W's number, you have an output. And because of that, you have the correct answer. You can measure the distance in what you call the distance from your results to the correct answer results. And so if you put and if you consider your W's as a dimension in a space, and you put an additional space and say that that is the height of that space that correspond to the error. If the nonlinearity satisfy some mathematical requirements, you come out with a smooth surface. So every set of W, so every set of numbers that you consider as a W correspond to a point in that surface in which its height is the amount of error you have made. So because it is smooth, you can follow some strategies to running down this surface to reach some minimum. And the process of running to that surface is the learning process. So you are learning because as you move with this in this surface, you are improving your performance because you are reducing your error. So now think about to what you do normally when you apply some algorithm that is statistical method, whatever. Normally you have a fixed amount of input. So this input, in this case, 3 input, say the height, the BMI, and the blood pressure, I don't know. And they are every time the same and they are fixed. But what about text? What about something that you don't know how many data you have? or some measure that you can take repeatedly, maybe in an hospitalization or somewhere. You don't know how many data you have, and you should have a strategies to manage inputs that have length of that can be changed. So think about your layers that put the output of those layers, and without changing the weight, as you can see, the weight are every time the same in a single step. You put your output as an input of itself on the side of the new stage of the input. So you can start to use every layer iteratively to train as much as needed for your sequence. So with this strategy, you can obtain models that can manage arbitrary sized sequences of input and also output. So you can have some, for example, classification algorithm that take a text of a not fixed length and come out with a single, I don't know, yes, no, include or exclude output. Or you can also have a different length in the output that can be the same as the input or even different output of input. So, for example, think about to translate your search strings from one engine to another engine, and possibly and quite surely the length of the search string for one engine is different from the other one. And also you can use a single input to have a varying length of output. Okay, so that was just for having a slightly overview of how machine learning works, but how can it benefit your systematic reviews process? So as we said, you could be to avoid some redundancy in your search strings. So for example, for synonyms in your search strings or name variation. And that is a kind of one-to-one or one-to-many models, because you start from one word and maybe you can have multiple synonyms for that word to be included in your search strings. And now many search engines already have something like some button on something that say something like, I have found 200 synonyms for your word. Would you like to add those to your string? And you simply push yes, and all the synonyms come inside your search strings. Obviously, and as we say later, every machine-assisted process is validated by humans or is driven by humans, because as we said, that is we are talking about machine learning that assists researchers, not substitute researchers. Okay, another aspect, or for the creation of the search string, you can also use the mesh terms that are medical search headings, and that are trained and extracted from the text using machine learning techniques that are human checked clearly, but they are systems that analyze the text, so a many-to-many algorithm that analyze the text and come out with possible headings for that text. And this comes in use. It is useful also when you have preliminary results on your search. So when you are creating and refining your search strings, because you start to collect some results, and if you like, you can put together in a clustering learning algorithm to highlight what are the similarities of those records that you have already retrieved manually that are according to your topic, to see what are maybe the keywords or the topic that you can use to create similarities between them. Next, for the searching, the effective searching stage, you, as I said, you can use machine learning to translate the search string from one source to another source. But even a more interesting aspect is when you have to translate a search string to anything, because maybe you would like to investigate a source that cannot use a search strings engine. And so we see an example in a few slides in which we trained an algorithm to apply the search string strategy used to retrieve records in PubMed to train an algorithm that can use a similar strategies, but that is not based on search strings to clinicaltrial.gov registry. And finally, with in the screening phase, you could be interested in filter out a specific type of general kind of records, something like I am only interested in RCTs records, so filter out everything else. Or you would like strategies to optimize your exploration of the record to select which are relevant and which are not. For both of those aspects, you have instruments, and in the first case, for example, when you want to exclude non-clinical trial studies, you have tools that works very well, and also you have tools for which you can be assisted in an active learning environment in which you are exposed to the most probable records of interest in the set of records you have retrieved, and clearly this draw a trade-off you have to accept and decide, because it is proved that you cannot reach the perfect machine, so you cannot be sure to have a perfect result if you don't explore everything you have retrieved. So as soon as you would like to save some times, and in this case it could be translated in don't explore all of your records, you have to admit that some kind of error, so some kind of maybe false negative in this case can be happen. So the rule of those systems like the ASR review is to expose you to what is in this moment in the unlabeled set, so in the record that are not already marked as relevant or not relevant, expose you with what it retain that is the most probable to be relevant, because the chance to come out with a not relevant record is quite 100%. So if you every time are exposed with the most relevant, you can continue to train the algorithm to perform better. And sometime and in some moment in this stage, you can decide, okay, I'm satisfied with these results I have obtained, and I'm sure that everything else is irrelevant. But as I said, this is a trade-off decision you have to make. Okay, about our case studies, the main problem is that for clinical trials, often only the published results are investigated. This because registries are quite difficult to be explored, because they don't have very powerful tools to combine search strings or to use search string. And with a research of Bodar et al. In the 2017, they reanalyzed 14 systematic reviews and meta-analysis that not involved clinical registries when they retrieve the records. And after slightly less than 2 years of work, they found that that is a very relevant problem, because including records from registries also come up to an additional amount of patients that span from 10% to 50%, and the changing in statistics that is more or up to 29%. So what is the strategy regarding what we have just said now today? We are in the searching phase, not in the screening phase, because we would like to take to apply something like a search string to clinical trial registries, that in this case is clinicaltrial.gov, and we would like to extract all the possible relevant records to be screened. So we are not screening record, but we are only selecting something like happen when you put a search string in PubMed. And this is a supervised passive learning, because we have all the answers, we have all the information in PubMed, and we don't want to update your knowledge. We don't need to update our knowledge. So we train a classificator, so a many-to-one algorithm that can that was trained on the PubMed records that for which we know which are the positive ones, because are the record that are considered positive in those 14 systematic reviews, and we randomly selected negative record for the rest of PubMed. So we train this system, and we would like to apply them to all the clinicaltrial.gov that is public, so you can download it, and we take a snapshot of it and apply all of that. So we follow this flowchart. I don't want to enter into the details because I'm slightly late with time, but mainly the training set is PubMed, the test set is clinicaltrial.gov, and we span through quite a great amount of option between machine learning techniques, parameters, balancing technique, because positive to negative ratio is quite important here, and we validate our strategy to have what the best combination of techniques, parameter and balancing techniques is. Next, we use those parameter, with that technique and with that balancing technique to retrain everything with all the system, because in the validation phase you don't use all your records, so you are underusing your information, and we apply our final trained system to the clinicaltrial.gov. And thanks to the work of Bodar et al., we have the right answer even for the test set. So we can evaluate the performance of our algorithm and get out with how well works our system. And what we found is that we left out a single record out of all of them found by Bodar et al. From all the clinicaltrials.gov. And even if that is not a quite important things, because the most important things is the time. So we don't spend years, maybe less than a month for write everything and train everything and predict everything. But even an additional gain is even for the next step. So the screening stage, because the number of records that we retrieve from clinicaltrial.gov as possible of interest are in half of the case less. So in half of those 14 studies is less than the record that Bodar et al. Retrieved manually for the screening phases. And even the ability to distinguish by our algorithm from on-topic and off-topic articles or records, not articles, range more. They are more than 90% of area under the ROC curves. Okay, so given that, what are the issues and challenges in this field? In my opinion, the first and most important things is the transparency. So we are used to see machine learning as a black box, and that is true. But the problem for me is not that the algorithm is a black box, is that often the procedure followed to create the algorithm is a black box. So the algorithms are not public, the data for which they are trained or in which they are validated are not publicly available, or they are very difficult to retrieve, or they cannot be used. So and even for validation, we need some ways to have to be sure that our measure of performance for our algorithm are trustable, and that's come with the strip to follow the FAIR principles that are findable, accessible, interoperable, and reusable object like data or algorithm or whatever. And all of that is important to make trust in what we provide. That in some ways they are blindly true. So there are cases in which we even don't ask ourselves if an algorithm is correct or not. Something like I don't know, Google search or Facebook something, or self-driving car, in which we are blindly agree with all machine learning machinery behind the scene that that are completely hidden from us. And on the other side, for our perspective in healthcare, correctly, we are very high skeptical. And this is mainly because I think the problem with the previous things, and because we think that machine learning can be applied to everything and can, as said yesterday by the speaker of yesterday, we cannot shoot things of machine learning and the panacea of healthcare for any kind of data, for any kind of problem. But we need to have tools in which we can have trust of them. And for that, another huge problem is that we have algorithms that come out and disappear as fast as they publish it often, because they are not shared, they are not usable by other people, they are closed in their development. And so starting from that, the International Collaboration for Automation of Systematic Reviews put out what they call the Vienna Principles, in which they state that machine learning is effective and can be helping systematic review process. And so all tasks of the systematic reviews can be and must be assisted by automation and machine learning. But also those tools should be continuously improved, because they can be continuously improved. And but in this improvement, you don't never change time or tools for standards. So you have to improve your algorithm and your process, but maintaining high standards of quality. And those standards can be achieved mainly only with collaboration with people and algorithms. So you have to provide and use algorithms that can be combined together, working together between groups of people and between tools and automatic tools. And everything of that should be shared for free, because we are talking about systematic review and meta-analysis that are on the top of the evidence pyramid of healthcare. And that means that these findings as the base on our healthcare. So are the base of the decision that drive people treated in some way or in some other ways. So they should be accessible to everyone in the world, and most part of the world can be afford fees or something like that for those automation. And the most important to be used that and to create trust on that is to create tools that can be reproducible and that you can evaluate in different environments in which they are developed. So to conclude, I put here some link in which you can find many tools that can assist you in systematic review. They are, I think, quite effective if you would like to explore some tools to assist you. And I thank you for the attention, and I drop you a quotation from Daniel Oberski in one of his interview that highlight how, as I said before, so if you accept only perfect performance, artificial intelligence is not for you, definitely. But I've heard that even humans have made mistakes. So the only thing that I would like to add to this quotation that is quite funny for me is that the main difference here is what is said before. So human can make mistakes, okay, but we trust in humans. The problem of AI for me is not that we know they made mistake, but the problem is now we have to create a system and an environment in which we can trust in AI, even if it makes mistakes. Okay, thank you.
Thank you very much, Corrado, for your enlightening presentation. And I think that I have a bit of conflict of interest because I've been working with you on this topic, also with Professor Berchiala. So I think it's very, very interesting, and we are actively involved into this. Well, I have I read the question from the audience, and I think that there is a very, very good one. Probably you, in a way, you already touched the issue. It is the trade-off between the human error and the machine error, because when we talk about machine learning, we are so concerned with the error that automation can introduce in the process. But clearly, there is also a human error when, particularly in systematic reviews, that may occur. So I would like a comment on this, and if possible from you, but also from Andrea Ricotti, that working as a biostatistician in a clinical unit maybe has also a strong feeling on that, a strong opinion on that. Corrado, if you want to start, if you want to reply.
Yes. So as also yesterday they discuss on the measure of error from machine learning techniques. In my opinion, that is a crucial aspect. So we need to, as I said, validate our algorithm, and mainly compare the results with the humans ones, because as you said, humans made errors, and machine made errors, and but I think also that one of the main problem is that from one side, so because of trust, the lack of trust, we don't consider the amount of error from one side. So even if machine can provide something with a huge less amount of error, we are prone to don't trust it. But from the other side, there is a good ground from that not trusting the machine, because in difference of humans, the machine can be biased in structured ways. So as one of the principles, in fact, today in developing machine learning algorithms is even to focus on structured bias, like gender bias or something like that, because we know that the errors that machine makes are quite never random, and that is not the case for humans. So it is true that machine can achieve higher performance than humans, but even if the errors are less, they are intrinsically different, and that for me is the main point. So in addition to what Ron Summers said yesterday, so that we need tools that we don't have to measure the uncertainty and the errors within the machine learning techniques. We also need to understand better how to detect systematic bias, because that, in my opinion, is the first step in giving trust to machine, because I can reduce by a huge fraction my errors, but if the errors stop to become random and become selective, especially when the results involves human, I think that it is not acceptable. So yes.
Thank you for your answer. We know that the view of the data scientist and the view of the biostatistician, assuming that there should be a bit of we assume that you may cover opposite corners in this answer.
But in my opinion, it's in my reality, to believe in machine learning for most of the clinicians like to believe in God. So it's something that they don't control, and it's difficult to understand why a black box can make some prediction or some results. And it's in my opinion, it should be better to teach the basic concept of the machine learning in the university, because they understand the 2x2 tables, but they don't understand anything further. So probably because in the literature, they are exposed to the basic concept of the statistics, not to the straightforward concept. It's a bias of...
Thank you. Thank you, Andrea, for your view. There is another question from the floor. Then Andrea Francavilla, which is a resident in medical statistics, says that today probably we are a little bit more optimistic with respect to the artificial intelligence and machine learning as compared to yesterday, where there was a little bit of skepticism about the potential of machine learning and artificial intelligence for some domains of healthcare, of health in general. And probably you remember that it was also another question from the floor, that probably the time for trustfully embedding artificial intelligence and machine learning into clinical trials is yet to come, because we are not enough confident in applying machine learning, for example, for the detection of heterogeneous treatment effects. So I would like to involve Professor Paola Berchialla, because she's an expert, and I think that she can help us to maybe to shed light on this if she wants to take part.
Yeah,
Paola,
I would just say, just a joke of what Andrea said before, that many clinicians, I mean, the more enlightened clinicians use SPSS, which is a well-known black box, and they usually trust in SPSS. So maybe because they, in a way, they can control the output of this black box, and so they trust in it. I agree with Andrea that machine learning should be learned at university, because this is the moment in medical students can understand the principle of machine learning, how it works, and how the output can be controlled. And in my point of view, we are moving toward using machine learning much more than statistical modeling. I mean, in the side of in many medicine fields, because I mean, I just was I want just to make a reference to the yesterday talk of Ronald Summers. We talk about radiologists, and also cardiology is an important field in which machine learning is taking room. And I just want to be more focused on the question of Andrea. I think that we are moving toward machine learning because we have a lot of data. We have more complex data than in the past, and we may, in a sense, we may get some new information for our data if we use more sophisticated models. And just is the way machine learning deal with data and join data, combine data, which is different from the traditional aspects of statistical modeling. And this is something really new and different. This is not a kind of choosing a method instead of another method, but is how to make data more powerful.
Paola, I totally agree with you, and I thank you for your reply. My question is why clinical trials do not trust machine learning enough? Is there more room to gain this trust in systematic reviews or in automation of in other health domains? I would say, when we talk about other applications, or not? Or at the end, we will be able to introduce machine learning even in clinical trials, and not only for text mining or other applications, other fields.
I'm just saying it's my personal opinion. So I think that sometimes it's our fault, because it is the way we explain machine learning and how we get from machine learning to clinicians. And so I think that they cannot understand the difference and what more they can get using machine learning than traditional statistical modeling. Because I understand that clinicians are usually used to add a given interpretation to data, and they learn classical tools like statistical modeling, which is not an easy thing to do. So they achieve some kind of knowledge and they want to use their knowledge. And machine learning is something completely different. I think that in this day we are in a kind of in between these two fields. And I think that we need to bridge the way we understand data with traditional models and the way we understand data with machine learning. And in this sense, I would be very curious about the topic on causal machine learning causal inference in machine learning, because it's a kind of bridging these two fields. But at the end, I think we need an effort from us, for statisticians, and from computer scientists to better explain these new tools and how they can give something more than traditional statistical modeling. And of course, in some application, statistical modeling is enough, and we don't have to think that one model is better than another, because it depends on what we want to get.
Yes. Right. The last talk will give us important information about the marriage of causality and machine learning. As we said before, there are different fields, but it's important to establish bridges. It's important to let one field contribute to the other. I think that there should be a strong interaction and not different positions that can be integrated, can be complementary. Well, there is another question that's very interesting question, as I said before, and I want to anticipate it. That is, from a practical point of view, which is the minimal sample size to apply machine learning as compared to the old statistical method. I would say that we can say old statistical methods because we get a little bit grumpy, as a beautiful Professor Frank Harrell yesterday. And well, Corrado, have you got an opinion on this? I would like to know your point of view.
Yes, as the as we just said, even before, the main issues here is that we don't have tools to measure the uncertainty, and so even evaluate good sample size a priori is difficult. In machine learning, the best strategy is to start as quick as possible, as fast as possible, and even with few amount of data, but maintaining track of the results and validating every step, and next to iterate the process with maybe more data. As Professor Tibshirani said yesterday, for us, computers are quite powerful and quite fast. So especially in our fields, often we don't have billions of data to manage. So our laptops or even our some server that to which we can have access are successfully sufficiently powerful to manage this iteration problem, because there is another aspect that as highlighted even yesterday, there are a huge amount of algorithms, and especially when we comes with the neural networks and even more with deep learning, the amount of customization you can provide to an algorithm is very huge. So it is completely not possible to explore every different network you can provide or every different set of parameter you can use. And so data are proved to be important, but they are not necessarily the most important things. So spending time, money, people to collect data, and I refer in collecting a big amount of data, because as even Professor Esangelini said yesterday, the main issues is collecting good data, but it's not necessary to start collecting huge amount of data. So we should start collecting good data in the amount that are manageable for us, and start our model, start to view the results, start to view the progression of the result, and to fine-tune our models or change model or validating our model based on these previous results, and so that we can know if we need more data, or if we need possibly different data, or if we need different information on that data. And earlier we know those information, the better it is for saving time or for better results. And yes, and that's come with the second aspect, in my opinion, important to this question, is that the aims, in my opinion, the aims of machine learning is different from the traditional statistical method. So maybe the overlap of the techniques can be huge for me. So I don't fix my point in difference. So which technique is to be considered as machine learning or as traditional statistical method, etc. But in my opinion, the distinction is on the aim. So when I apply statistical method, I have my set of data, my data on my patients, for example, and I would like to extract some insight of them. so to know something about them. And while and so that it is very important, the parameters and all the metrics we have in those cases. But in machine learning, we often we have a product that do something, not that explain something. In fact, the problem of explanation in machine learning that can be solved is, oh, okay, I have a result. What caused that result? And that is the standard question. What caused that result? Why machine learning do that things? And we can roll back the algorithms or use some tools, and we can have some insight of what cause of that. But in my opinion, the question is wrong. So you use machine learning, as we said, for example, in assist for screening or for searching in systematic view, to achieve a result, not to explain something. So you have a tool that can assist you to achieve a result. And so the metric in this case is what is the level of good for me, for what is a good level of performance for me in that result, for that result. And so I can answer to that starting from small amount of data, try to produce a tool that give me a result. And as also professors, all the three professors says yesterday, we should start simple. And we should start simple, and with the data we can have, considering the overall amount of time we would like, or the resources we would like to put in the game, and so
it's very nice explanation. Thank you very much. But I would like to move on with the next speaker, which is Rachael Phillips. We just make a small switch in the schedule because the other presenter is experiencing trouble with her connection. So welcome, Rachael. Thank you very much for joining us. It's very early in the morning there, so thank you very much. It's my pleasure to introduce Rachael Phillips. She's a PhD student at the University of California, Berkeley, and she's a PhD student in Biostatistics, mentored by Professor Mark van der Laan, and her research interests include causality and machine learning, particularly targeted machine learning, and she's now also working on a project involving machine learning with the Food and Drug Administration, the US, with the FDA. So, Rachael, thank you very much. You have the floor.
Thank you very much for having me, Ileana. And I'm sorry I am not Mark. He is my
No, it's a pleasure to have you here, and thank you very much also for Mark who decided to recommend you. We are grateful. Thank you very much. You can share your presentation.
Okay. Can everyone see my screen?
Yeah.
not the full screen one. We are still viewing the main screen.
Let's try this.
Probably you have to switch into the presentation mode.
Yes, I think I needed to share my entire desktop.
Okay, now we see the presentation. Thank you.
Okay. So today I'm going to talk about targeted learning or targeted machine learning and how we can use this tool to bridge together machine learning with statistical and causal inference. Thank you very much for having me. I'm going to try to move this dash so I can see the slides. Okay. Okay, so here on the screen, we have a flow diagram showing how we might start with a causal question, use causal frameworks to get to a statistical target, and we can use machine learning and targeted learning to approximate the answer to this statistical estimate. What this figure shows is a few different things that I want to point out. First, with this orange box in the causal question, we can use causal frameworks to minimize a causal gap or causal bias. This is a bias that's due to departures from causal assumptions not holding in our data. After we've translated the causal world in the causal question into a statistical question or into a question that can be estimated from the observed data, then we have something that's statistical. This is our classic data analysis. We can use what we've empirically found to approximate the answer to a statistical question. So the causal world and the observed data world exist separately, but we can connect them using causal identifiability assumptions. And we'll talk about this a little bit later too. So we can use machine learning and targeted learning once we have the statistical target to get as close as possible to the truth. Specifically, what we can use targeted learning for is to obtain inference for a low dimensional target parameter, like the average treatment effect, odds ratio, relative risk, whereas we can use machine learning with targeted learning to approximate higher dimensional functionals that are necessary to evaluate a target parameter. So in this talk, we'll go into some causal frameworks and then how we can tie that with the machine learning and targeted learning. There we go. Okay, so targeted learning is a subfield of statistics, and I've included 2 books here on targeted learning. The first was written in 2011, Targeted Learning for Causal Inference and Observational and Experimental Studies. And then here we have something that was more recently published and is more advanced, that focuses more on longitudinal settings. And I highly recommend this book. The first 6 chapters, including the preface, were a great learning resource for me to understand this field in greater depth. Okay, so there are several real-world applications of targeted learning, and I've included a few article titles here. So we can use targeted learning in observational data and in experimental or randomized controlled trial data. These examples incorporate a variety of this. So here, this was a study that looked at HIV testing in community health in rural Africa, and this was a community randomized trial. And then here, we're looking at vaccine efficacy of a malaria vaccine. This study is it's a good example of how we can use targeted learning, in particular the superlearner algorithm with observational data to learn a prediction function for predicting mortality. And then here's another example in the healthcare realm, looking at variable importance analyses of medical conditions for healthcare spending. So this is a nice illustration of how targeted learning can be used to make better clinical decisions from observational data. This study is looking at the comparative effectiveness with time-varying interventions. In particular, this intervention was trying to identify when to intensify glucose control for patients with diabetes. And here we have a image of some results using standard methods, which found that there was no benefit to intensifying glucose levels aggressively. When we used targeted learning, we saw more of a spread of how earlier intensification of glucose control was helping patients survive longer. So with targeted learning, we can, we'll see what we can do and let the data really speak for itself without assuming some sort of parametric form or model that is not realistically covering the true data generating distribution. Okay. So here I have an image showing how real world data can induce challenges, and we'll see how targeted learning can be used to address these challenges. So in this top panel, we have kind of a increasing degree of the amount of real world data that's being used in a study. And this image here was borrowed from a slide, a webinar that was given about using real world data in the FDA. So even in clinical trials, regulatory decisions are increasingly being made using data that is based somewhat on randomized trials, and then also pulls in observational data from external sources. So here are a few examples. Using real world data to assess enrollment criteria and trial feasibility. So using observational data to enroll patients into a randomized control trial or to support site selection. Another way we might use real world data is if we have a single arm study with an external control arm. Say if we randomize patients to receive a experimental drug and we randomize much more of them to receive the drug, then we can pull in more controls by using an external control arm or historical controls. So there are ways that real world data can be integrated in these regulatory studies to make decisions. And here are some of the challenges with integrating real world data. We might have selection bias or intercurrent events, which are events impacted by the treatment that occur after it's received. We might have informative missingness or informative loss to follow-up. Treatment by indication, high dimensional covariates, such as covariates from electronic health record data or covariates derived from natural language processing. There's outcome measurement error, statistical model misspecification, and then there can be differences between external controls and single arm trial randomized control trial subjects. So we'll see how targeted learning can support the path to regulatory decision-making and address these challenges. In particular, we can use the targeted learning roadmap, which is a systematic procedure for designing and evaluating real-world studies. Here are the steps of the roadmap. This is quite general, just a roadmap for learning from data. And this has been really important to me and others who are trying to evaluate, design, or analyze a study. So first step is to describe the experiment. With the knowledge about the experiment, specify the statistical model. Then we can define the statistical query or the question of interest that can be learned from the observed data. Step 3 has an additional component. If you have a question that is of causal nature, so if you want to know the cause-effect relationship, then step 3 might involve causal inference as well, which in our example, it will. Step 4 is to construct an estimator to estimate the answer to this query, then to obtain inference for the estimator, for the estimate, and to make a substantive conclusion, which might include a sensitivity analysis or an investigation looking into departures from the causal assumptions. Okay, so step 1, what is the experiment that generated the data? Each of these steps, I include a motivating question that should be answered by each step. So this is the question for step 1. And going through the roadmap, I'm going to draw on an example This was a study that looked into the impact of corticosteroids on mortality among patients in the ICU that were in septic shock. This is one of the most frequent and dangerous events that can occur in the ICU, and it can cause organ perfusion and hypotension. Okay, so there were previous study results that used more traditional methods, and they were meta-analyses looking into large amounts of RCTs and then trying to assess the relative risk for mortality. So how much corticosteroids impacted mortality compared to no corticosteroid treatment. Each of them found a null effect. We can see their confidence intervals here are overlapping the null of relative risk of 1. Okay, so we're going to use the same data from the RCT of the previous meta 3 RCT. This includes 1,300 adults, and our target population is adults in septic shock from these 3 randomized control trials. So this is an example of what the data might look like. We have some baseline factors that we assess for each subject, like body mass index, age, sex, and then we randomize the subject either to receive the corticosteroids or not. I'm using 1 to denote that they did receive the steroid, 0 to denote that they did not. And then we can measure the 1-month mortality, whether or not they died after 1 month of receiving this steroid treatment. 1 denoting that they did, and 0 that they did not. We can use a directed acyclic graph, which is a tool borrowed from Causal Inference, to understand the relationships between the variables and how they connect to each other. So classically, a DAG also has an arrow from W to A, but we have a randomized trial in this setting. So pretreatment covariates are not impacting the treatment decision, whether or not someone receives steroids, because that is a randomized decision. And we can still use targeted learning for observational data. This example just is a randomized setting. So we want to assess this arrow here, the effect of the steroid treatment on 1-month mortality. And we have a meta-analysis. This is a pooled sample. Okay. So we've described the experiment. We know that there are baseline factors and that the treatment was randomized. The next step is to specify the statistical model. And the motivating question is, what is known about the stochastic relations of the observed variables? So I just said what we know. We know the treatment is randomized, and we know that we have these pretreatment covariates that might also impact 1-month mortality. We might, if the treatment was not randomized, we still might have some information about the way treatment was assigned. If a doctor says, I only consider these few variables when I'm trying to assign treatment, then we can use that information provided by subject matter experts in our specification of the statistical model. If we know that there is some sort of conditional independence across units, like units are connected through their friends or just their friends of friends, then we can use this kind of structure to create conditional independencies in the data as well. So really things that we know about the experiment that are reasonable, realistic, and don't assume some sort of functional form unless that's known like physically or through the subject matter realm. So what we want to show, what I'm showing here is that we want to specify the statistical model to be realistic. By that, I mean, it should contain the true data generating process. In specification of a realistic model, we pretty much guarantee this because we're only including knowledge that is known in this specification. Something like a parametric model is more restrictive, and it assumes that the data generating process can be modeled by a finite set of parameters. So these often are misspecified and do not contain the truth. Why does that matter? Oops. So what happens if the statistical model is misspecified and does not contain the truth, which is like we are seeing here. Well, as sample size increases, you're actually guaranteed to find significant results that aren't there. So your rate of false positives is going to increase. And then 95% confidence interval coverage, or the chance that your 95% confidence interval actually contains the truth, will decrease with increasing sample size. This is because as the sample size increases, your confidence interval will get narrower and narrower and narrower, but this won't be around the truth because the model is misspecified and you're not actually approximating the truth. Okay, so we're going to make sure to specify the statistical model realistically, so we don't have this sort of inverse relationship with what's supposed to happen in statistics. The next step is to define the statistical query. In this example, we are going to use a causal inference framework to identify the target causal estimand that we aim to identify from the data. So in this example, we have an additional step of going from the causal world to the statistical world. And this is common in experimental studies, but you can also do this kind of thing in an observational data analysis as well. So our motivating causal question is, what is the causal risk ratio in mortality between treatment groups? And here I've defined the parameter, which I use subscript causal. Okay, so what does this look like? This y sub 1 here is a counterfactual outcome, and it is the outcome that would have occurred had all the subjects received the steroid treatment. So what would have been the probability of mortality if all the subjects had received the steroid treatment? Y sub 0 is similar. It's the counterfactual outcome had all the subjects received the no steroid treatment. And this probability is the probability of mortality had all the subjects received had not received steroids. This is, and by all the subjects, I mean those in the target population, which we specified here. Okay, so here's how our data might look if we wanted to look at these counterfactual outcomes. These causal target parameters are functions of this full data under the intervention of interest. So here we can see the same data as before. I've just started to use the notation. Here's the treatment, 1 month mortality that we observed, and then the 3 covariates that I introduced earlier. I've added 2 columns for the counterfactual outcomes. Causal inference can sometimes be described as a missing data problem, and this is because we don't observe both counterfactual outcomes for each subject. We only observe one of them. So this full data structure is something that we don't have in our observed data, but it's something that we'd like to approximate in order to understand the answer to this question. So causal identifiability assumptions are what's needed to identify this parameter from the observed data. So how can we use our observed data to approximate this parameter? The first assumption that we need to hold is no unmeasured confounding or randomization or conditional changeability, which is sometimes just called exchangeability. In a randomized trial, this is going to hold because we've randomized the treatment decision, so we don't have covariates that are impacting both the treatment decision and the outcome. There is no unmeasured confounding. However, in an observational study, this might not be true, and we can use a sensitivity analysis to violate assumptions, to investigate violations of this assumption. This is something that also cannot be tested from the data, but it's something that you can assess based on knowledge about the study, talking to subject matter experts about whether or not they think all of the variables that could have impacted both the treatment and the outcome are present in the observed data. This assumption is necessary in order to interpret our estimate causally. So in order to say that what we found is an approximation of a cause-effect relationship, we need this assumption to hold. Even if it doesn't hold, it's worth mentioning what would have been necessary in order for it to hold, and how it might not be justified or how it could be justified. So in interpreting results, it's important to discuss these assumptions and justify them. Here's the other assumption, which is referred to as positivity or experimental treatment assignment assumption. This assumption is also necessary to interpret the estimate as a cause-effect relationship. It's also necessary to define a well-defined statistical estimation procedure. The positivity assumption states that there's a positive probability of receiving each treatment type that there is. This is also guaranteed in a randomized trial. Each subject had the same probability of receiving the treatment because it's randomized. If it's the case that some subjects, there's no way they could have received the treatment, then this assumption would have been violated. And there are studies that look into what you can do when there are violations of the positivity assumption. An example is to restrict the target population or to define a realistic intervention, which basically says that if the patient could have never received the intervention, then I'm never going to try to intervene on them. Or just saying, I'm going to restrict the target population to those subjects that could have received either intervention. So that way we're making sure that this assumption holds. This is something that we can actually look into with the data, looking at a plot of the propensity scores or the probability of receiving treatment. We can estimate that and see if there's overlap between the two different treatment groups to see how different they are, and if each subject does indeed seem to have a positive probability of receiving either intervention. But like I said, both of these hold already in the randomized trial setting. When both of these assumptions hold, the G computation formula tells us that we can approximate the post-intervention distribution defined by this full data in terms of the observed data distribution. So here I'm showing a simplified version of the identifiability result that would be needed and what the G computation formula will give us. So we can define this causal parameter in terms of our observed data if these assumptions that I mentioned on the previous slide hold. So now we are back to the statistical world, or the world of the observed data. This is what we actually can use to approximate the answer to our question. And the question here is reworded slightly. What is the risk of mortality between treatment groups when adjusting for covariates? We could have just started out with this question as well. You don't have to have the causal question. That just tends to be the case in most scientific studies, is the motivating question really is assessing some sort of cause-effect relationship. So here is the statistical estimand or observed data estimand that we will estimate from the data. And this is the motivating question. What is the target statistical estimand that we will learn from the data? Okay. Step 4, constructing an estimator. So approximating the answer to this statistical question. And the motivating question, how should we estimate the target estimand? Here are some statistical properties that we might want to consider when deciding on an estimator. We might want to choose an estimator that is a substitution or plug-in estimator. That way we can plug in the result into the target parameter mapping. This guarantees that global bounds on the statistical model are met, such as monotonicity, or if our answer should be a probability, we will be getting a probability as our answer. Also valid inference, so being able to construct confidence intervals and get p-values that are accurately approximating the uncertainty in the sampling distribution of the estimator. Efficiency, or having the lowest possible variance that we can for our estimator. This is basically saying that you get the most bang for your buck, having as few of subjects as possible, but getting the most narrow confidence interval that you could. So efficient in terms of using the data all the data that you have in an efficient way in order to really get the narrowest confidence interval that you can. Also, the ability to optimize finite sample performance. So we want estimators that not only behave well in theory or as sample size grows to infinity asymptotically, but those that we can tailor the performance in finite samples as well. Okay, so one choice of estimator that we would recommend is targeted maximum likelihood estimation, or TMLE. These estimates check off these qualities that I was just mentioning we might want to consider. They're plug-in estimators, efficient, unbiased, and finite sample robust. So there are augmentations of the TMLE estimator that we can incorporate, like higher order TMLE, collaborative TMLE. These things are designed to optimize finite sample performance, and they can improve finite sample performance. Asymptotically, they don't make a difference, but in finite samples, they have been shown to improve the TMLE. So what is involved in this process? It's really can be broken down into two steps. The first step is the machine learning step. It involves estimating our prediction function of interest, which is the probability of dying given A and W, the treatment and the covariates. We'll estimate this prediction function using superlearning. Then we will update the initial estimate to achieve the optimal bias variance trade-off for our target parameter of interest, which is this low dimensional representation, the relative risk of mortality under the corticosteroid treatment. So TMLE step one is the superlearner. What the superlearner does is it's an a priori specified and data adaptive estimator that involves specification of a library of algorithms that can range from very simple, like a simple parametric model, to highly complex, like a neural network. And we want to make the superlearner library as rich and diverse as possible, with the ability to handle high dimensional data, to be diverse with regard to the learning strategies, and to be as rich as possible. You can also include the same learner with different hyperparameter specifications. This might be of interest in more complex machine learning algorithms like neural networks, where there are several ways to tune them. And we want to consider multiple tuning parameters for the same machine learning algorithm. Once we've specified this set of machine learning algorithms and a cross-validation scheme, then we can create this competition between the learners and choose the one that has the best cross-validated predictive performance. In this example, the learner that had the best cross-validated predictive performance was actually an ensemble of highly adaptive lasso, Bayesian additive regression trees, and a generalized linear model. Cross-validation sets up a playing field to evaluate the performance of these estimators. And this is an example showing tenfold cross-validation, where we have our learning set of data. We split it into 10 different subsets that are independent from each other. And then we can train these algorithms on 9/10 of the data and evaluate their performance on 1/10. This is just one possible split. You could also have the dark gray or the validation set be here and 9, and then so forth all the way to 1. And indeed, that's what the cross-validated predictive performance is we would have 10 of these constructions alternating what the validation set is, and we can use this cross-validated predictive performance as a way to optimally select an estimator. Okay, so here we have a visual showing how targeting follows a maximum change in target estimand per unit likelihood. So what this is showing is that this orange line here, which is the targeted estimate of the parameter, how it's changing the target parameter with respect to solving the average treatment effect in this example. So we can see that the slope of this line is greater. We're getting the maximum change in target parameter. And if the superlearner estimate is already very close to the truth, then of course the update won't do very much. In this example, it's a little bit further away. So the targeting has more of an effect on the change of the estimate. Okay, so what this targeting allows for is it allows the TMLE to behave as a sample mean of the efficient influence function. This means that we can approximate the variance of this estimator and it's through its sampling distribution. And so we can actually obtain formal inference for the target parameter of interest, which was this relative risk. And we can do that because we've designed the TMLE in the targeting step to update the machine learning estimate in an efficient way, in particular to solve the efficient influence function. And this allows our estimator to behave as an asymptotically linear estimator for which the sampling distribution can be approximated. Here in the plot, I'm showing the results of the previous trials alongside what we found with the TMLE that used the same data as this study. So we can see that we can really see the efficiency here where the confidence interval is narrower than the other two. And the TMLE results showed us that there actually was a lower risk of mortality in the corticosteroid treatment group. So here we found a significant effect of corticosteroids on reducing 1 month mortality among septic shock patients. Okay. Now that we've obtained inference for our estimate, we can make the substantive conclusion. So that can involve different steps. Here we're looking at a sensitivity analysis. That's one way we can arrive at a substantive conclusion, investigating causal bias with a sensitivity analysis. So causal bias is the gap between the estimate and the truth due to violations of the causal assumptions, like unmeasured confounding. This is something that cannot be tested from the data, but we can use a sensitivity analysis as a tool to investigate how much unmeasured confounding would be needed in order for our results to be deemed null or not null. Okay, so here we have two different studies, and both of them happen to have the same true causal quantity. Real world data study 1 has a wider confidence interval than real world study 2, so probably a smaller sample size. Here we have the estimated statistical quantity and then the true statistical quantity. This is just random variation between the two. And here there is no causal bias. The statistical quantity is the same as the causal quantity. The same is not true in this real world data study 2. The statistical quantity is further away from the causal quantity, so we do have this causal bias. And we can use the sensitivity analysis as an assessment of how departures from causal assumptions would impact the study findings. Let's see how that would look. Okay, so here is a non-parametric sensitivity analysis of an example with 25% loss to follow-up, which is abbreviated to LTFU. Okay, there's a lot going on in this plot, so let's look at each different component. Here, circled in gray, we have our estimate and a 95% confidence interval from the main analysis. Then in green, we have different estimates and 95% confidence intervals, which are just increased slightly. And then again, red, different estimates and confidence intervals, which are decreased slightly. In particular, we have this negative 0.5x, negative 1x, negative 1.5. So what we do is define what this x is, or a delta that we can assume is the causal bias. And the way that we define different levels of causal bias is that we looked at the difference after adjusting for measured confounding. In particular, ran an analysis without adjusting for any confounders, and then ran an analysis where we robustly adjust for confounders. The difference between these two estimates is 0.68. So we use this as our X. 0.5 times 0.68, 1.5 times 0.68, and then we would add that to our target parameter in order to see how much causal bias relative to the difference between unadjusted and adjusted estimate would be necessary in order to reach no effect. So here we have this gray dotted line, which represents no effect. And we can see that we don't get to that point until here. So if the unmeasured confounding is 5 times more powerful than our measured confounding, that's when we would see a null effect. So what's nice about using this 0.68 is that it shows us what difference is made after adjusting for measured confounding. So it's a nice way to parallel how much unmeasured confounding would be necessary relative to the measured confounding. And this is just one way to define a causal gap. We can also use subject matter knowledge, but this is actually kind of hard to think about how much measured confounding is present and how much unmeasured confounding is present, and then quantifying some sort of degree of it. So it's nice to have some sort of rule like this in order to do a sensitivity analysis. Here is another example of a sensitivity analysis. This one looks at a safety analysis example, and we have the relative risk. This is why the confidence interval width is changing, because we're on the log scale. So here in this sensitivity analysis, the main estimate and 95% confidence interval showed that there was no adverse effect of a treatment. So basically that the treatment was safe. We wanted to look into a sensitivity analysis to see how much unmeasured confounding would be needed in order for this drug to have adverse effects and to not be safe. So again, we looked at the difference between the TMLE and the unadjusted estimate to examine this difference, 1.08 to 0.87. That is our X. And so we can look at the assumed causal bias relative to the difference between adjusted and unadjusted estimates. And we see that not much unmeasured confounding is needed relative to the measured confounding in order for this treatment to be deemed not safe. We can see that the 95% confidence interval doesn't include one when we just have 2 times greater unmeasured confounding than measured confounding. And safety analyses are often based on observational data. So this could be something that would motivate regulatory agencies to reevaluate the safety analysis, maybe to try to use natural language processing to derive more covariates and try to investigate confounders more so. Okay, also in making the substantive conclusion, we have the possibility to refine our question of interest and inform future studies. Interestingly, in this study, we found that 2 different groups of people responded to the corticosteroids in very different ways. So we can refine our question to what subgroup of patients in septic shock benefit from corticosteroids. And we found that patients who did not respond to the stress test did not respond well to the steroid treatment and shouldn't be given steroids, whereas patients who did respond to a stress test did respond well to the corticosteroid treatment. So what this roadmap did is it took us from the beginning of our description of the experiment and then all the way to the end, where we ended up refining our question and finding out something new that is potentially impactful in corticosteroid treatment assignment for septic shock. Okay, so back to our slide from the beginning, targeted learning with real world data. We talked about these challenges, and then here are some ways that targeted learning supports regulatory decision making. So we have this procedure for statistical and causal inference, in particular this roadmap that allows us to define in a principled way what's happening with the data and how we can use the data and what we know about it in order to accurately approximate the answer to a scientific question. We use a realistic statistical model in order to avoid statistical model misspecification. Our statistical estimand can approximate the answer to a causal question. We use flexible estimation and dimension reduction with the superlearner and can incorporate a model-free sensitivity analysis and generate real-world evidence RWE with confidence. So ongoing applications with targeted learning, sequential adaptive randomized control trials. So adapting the probability of receiving a treatment over time so that people who are really benefiting from the treatment are more likely to receive it as a trial goes on. And this is a very efficient way to design a randomized control trial. Also online learning from data streams, in particular from wearable devices or mobile devices. Causal inference for networks, or when one person's treatment affects another person's outcome, how can we assign an independent structure in this setting and do statistical estimation? Causal effects of site-specific randomized control trials, and learning from electronic health record data for better control of confounders. So here are some active targeted learning collaborations and software. There was a recently developed research center for targeted machine learning at UC Berkeley, and this is the website to look more into that. Collaborations with government, the FDA, and the National Institute of Allergy and Infectious Diseases. Also, a lot of targeted learning is being applied in the private sector, from pharmaceutical companies to media companies like Netflix and Pandora, and healthcare as well. And then here is a description of some of the software that's available for targeted learning. There is the TLVerse software ecosystem in R, and here's the website. And then there are also software packages on the comprehensive R archive network, like TMLE, Superlearner, and then LTMLE, or TMLE for longitudinal data structures. Okay, and that's what I have for you today. Feel free to email me to ask questions, request more learning resources or anything, and thank you very much for your time.
Thank you very much, Rachael, for your very interesting presentation. And there are a few questions for you, but all those related to natural language processing and coupled with PLMA will be addressed at the end in floor discussion, because I think that there are good links with the next talk. There is a technical question for you related to multiple imputation. How can we deal with multiple imputation including this step in the TL roadmap? Is it possible to combine all the imputed data sets? How? Already implemented, soon to be implemented?
Yes, so the answer is it depends, but I can explain a little bit more. It depends what we're trying to impute. If we have loss to follow-up, say, and we have missing outcomes, that's something that we wouldn't recommend imputing. We can actually account for missingness in the outcome, similar to inverse probability weighting, how you can account for censoring and missingness of an outcome. So you don't need to impute a missing outcome, because we can just directly account for that in the estimation procedure. When we have something like covariates that are missing and they need to be imputed, that's completely fine. You could use a multiple imputation framework or some other form of imputation. But I want to note that if you do imputation, which happens all the time, we always have missing data. If you do this imputation procedure, before doing it, for each covariate that has missing values, add an extra column indicating whether or not that value was missing. That way you have a covariate that tells you which values were missing and which ones were not, and that can be used in an additional way as a covariate for fitting. So yes, you can use multiple imputation to do the imputation. I just recommend adding an additional covariate to indicate this missingness pattern.
Thank you very much, Rachel. So we move on to the last speaker, Professor Graciela Gonzalez. Graciela, are you here? Can you hear me?
Yes.
I would like to briefly introduce you. Thank you very much for coming, for being here. Professor Graciela Gonzalez is an outstanding scientist, recognized expert in the natural language processing domain, and she's professor of informatics at the University of Pennsylvania, where she's a faculty member since 2016, and there she established the Health Language Processing Center, and she has authored hundreds of publications in bioinformatics applied to the health domain. So Graciela, thank you very much, and you have the floor.
Thank you so much. Apologies for the misscheduling here, but here we are. I am really, really happy to be with you and to have this opportunity to celebrate with the University of Padova, the 800th anniversary, which is kind of like my book. So, and I come from an institution, I'm at the University of Pennsylvania, which by US standards is one of the oldest universities in the nation. It's actually older than the United States itself, since it was established before the country. So anyhow, but old in the US is just very young for your standards. So thank you so much. My talk today is gonna take a little tour of some of the research I've done with my group on mining real world data for health research. So I direct the Health Language Processing Center at the University of Pennsylvania in the School of Medicine. So I do natural language processing, focus entirely on health data, 24/7. So that's a field or a focus that I want to emphasize. We don't see natural language processing as merely a tool. It is a enabler of this new field or of this area of digital epidemiology. So basically, digital epidemiology is just like traditional epidemiology, but it uses data that was generated outside of the public health system. So it was not generated, this data that we use is not generated with the primary purpose of doing epidemiology, which means that it will have a lot of noise, you'll have a lot of challenges inherent in it. The studies themselves will have the same goals as typical epidemiology. We require access to large data sets and advanced analytics. And the challenge remains, aside of the technical challenges that come inherent to using this data, particularly in my case, the unstructured portions of data and free text and other postings, presents a challenge always for privacy and ethics. So that in itself is a whole other talk. The ethics of using this has been questions, and there's always this questions of whether we should use it. There have been some studies. I wrote an invited presentation at the National Library of Medicine as a blog, musings from the mezzanine, that talks about these issues of ethics, and there have been other papers published on it. So for the rest of my talk, all the studies that I'll present were cleared by the Institutional Review Board and abide by the ethics, not strictest ethics, I will say, because I do take care of going by the terms of use of Twitter, and also the dictates of common sense. Okay, so when we share data from Twitter, we try to be very, very mindful of the implications that sharing could bring to the user. But all that aside, so digital epidemiology presents many, many challenges. For real world data in particular, we want to focus on data that relates to the patient status. So this is the FDA definition, the United States Drug Administration, Federal Drug Administration. So they monitor and dictate a lot of things that you can do. They've been pushing for the use of real world data for regulatory purposes. So they want this data that relates to the patient health status or the delivery of healthcare routinely collected from a variety of sources, not just specifically for the purpose of epidemiology. So this includes electronic health records, claims and billing activities, product and disease registries, patient-generated data, that's where social media will come in, data gathered from other sources like mobile devices and monitors like that. And what they want is that they want real-world data that can be turned into real-world evidence. So they are already using some of this post-market safety and adverse events regulatory activities and data to use this to make these decisions. So so this is where all of this is directed. So we want to have the right methods in data collection, the right methods in data analysis, systematic data analysis, so that we can call the evidence derived from real world data, real world evidence. So it requires very, very systematic mining. The attractiveness, I guess, of many of these sources, in particular in this case, social media for us, is that it does reflect unfiltered the views of the patient, in this case of the user in general, and it's as real as it gets. So in the United States, for example, we looked at social media, all ages are represented, and actually the percentage of those older than 50 is growing through the years. And so there's not that big divide that used to be at the beginning, like into the 2008, 2010, where most of the data will come from the younger ages. So the age span has grown over time. In general, 79% of the US population uses some sort of social media. Worldwide, this is about 45%. I suppose in European nations, it's something similar to the US, 79, 80%. Most importantly also, the amount of time that is spent in social media, either producing it or consuming it, is about 3 hours per day. And I don't think this number is going to surprise anyone here anymore. Particularly with the pandemic, we've seen like an explosion of this time. And I actually think that this time might be a little bit underestimated at this point. So that means, why do I emphasize the time? Because there's a lot of information that flows in that amount of time. So if we get each and every one of this 79% or 45% of people producing or consuming information, there's a lot of knowledge that is exchanged. So we want to be able to capture it. This is a simple, very simple search I did specifically to illustrate some of the points of gathering data from social media. This is in response to "I've been diagnosed with," in quotes. So just to see what people say when they are being diagnosed with something. So it can be very long or very rich post, like the one you see here that says "I've been diagnosed with obsessive compulsive disorder," mentions anxiety as well, been on therapy for 2 months. So some of the internal feelings of this person are expressed right there in publicly available data. And this is on top of another one. So stories kind of pile up. Sometimes the original post generates many more of the same stories. At the same time, if you go to the next tweet that we see here, it says, "I've been diagnosed with a chronic fear of giants," which I think is said in jest. So it's not really a diagnosis, we want to think. Try to think of this from the automatic NLP perspective. So this will look exactly like the other one at some point in time, but then you have some other features that will allow you to classify it as not really a true positive in this case. We will hope. So we can, there are some features. We see some of the emojis. We see some of made up words that might not be recognized, although for an NLP system, that doesn't mean anything because many of the health data or health keywords really are not in dictionaries, or it will be misspelled. So that might not be the distinguishing feature. So the change in sentiment will be another one. So the diagnosis of something is typically, or we will hope, be put as a negative sentiment, for example, but then the last sentence is a happy one. So anyway, so there might be some features that can be derived from this. And then there's very sparse tweets that basically there's not much to go with. So that last one there, I've been diagnosed with OCD. It is, for humans, probably a true positive. It is a true diagnosis, but it might be a little bit ambiguous for an automatic classification. So just like that, so as I said, this was straight from Twitter. This makes us see that the information that will come from the public, we should never lose track of the fact that all of this comes from people. So the people behind Twitter are the ones that should occupy our minds in trying to design these studies and trying to get the right data at the right time for the right topics. We have to be careful in that in generating our cohorts, we're not being fooled by some of the tricks, I guess, or some of the roadblocks in social media, where things seem to come from different people, but in reality, they will be from the same group. So it can be done in images. It can certainly be done in data. So filtering and being careful with the way you treat data will avoid some of these pitfalls. So what I wanted to spend most of our time on is on a study. This is the longest running study that I have in my center. It's a study on pregnancy. It is pretty unique in that we use social media in a slightly different way. Most of the studies that you see published by necessity or because of the way research runs, they usually take a one tweet approach. So you find tweets that have a certain topic, a certain number of keywords, they collect them, and then they do the study on single tweets. It is the number of studies that use longitudinal data are much less. This is one of them, our set of studies actually. We've been running this since 2015, this collection of pregnant women, formally since like about 2017, where it got like a little bit more stricter. Our first paper was published in 2017 on this and how to form this cohort. And then we've been following the cohort since. So we have about 500,000 pregnant women collected over actually 7 years. 5 years was since or more strict definition of it. And it has allowed us to do many studies, and some of them are ongoing. This illustrates how a little bit of it and how it happens and how long it takes. So our first study in 2017 allowed us to get a cohort of which users, Twitter users, we would like to include. And so you see tweets like the one there from 2016, which is November 7th of 2016. Sorry, the July 11th of 2016 tweet. It says, it's time to announce that I'm having a baby and it's going to be a boy. So pregnancy announcements is the way that we get this cohort. So self-declarations. In all my work in forming cohorts, I always lean towards self-declarations rather than any inference. So we do not use inference. We always use self-declarations. This includes cohorts that we've collected lately on, for example, men who have sex with men and declare their gender identity openly on Twitter. And that's the way we capture it. So we always lean towards that. So in this case, it's self-declarations of pregnant women saying that they're pregnant. That single tweet also tells us the gender of the boy or the going to be a boy. So we have some information, but very limited. So we have the date when it's announced. That doesn't tell us much. All it does is allow us to add this user to our cohort. And then we go collect all the publicly available tweets by the same user. So depending on when we're collecting, we could very soon see the due date. So now we detected the due date being November 7th. So with that, we can calculate the pregnancy timeframe. So we have a system that calculates pregnancy timeframe, giving one or more, plus 1 or minus 1 months. So we get pregnancy timeframes of about 11 months. And thus, if we have tweets in that timeframe, we now have a user that we can use in our studies. Because we are very interested in information that happens in the periconception period and then throughout pregnancy. We have the birth of the baby right here on November 13. And a month later, and this is where we always like capturing or studying these windows of time, we see a reference to a birth defect, which is Hirschsprung's disease. So in a single timeline, we do, and this is obviously there's more tweets in between, and we have to have classifiers for it. So the whole pipeline for processing this includes many parts. So from the Twitter API, we get a cohort of pregnant women, we get their timelines, and now we can analyze, in this case for this study was birth defects. It is important also to get a comparator group. So in our first study of this type, it appeared in drug safety in 2019. Look at the time lapse, it's 2 years. It took us about 2 years to complete some of this. And this is a full-blown lab. I mean, I have 3 staff researchers, and I have annotators, and I have a developer. So it takes time, and it takes a lot of the systematic approach and analyzing the data. And in 2019, almost at the same time, we also published the process in Nature Digital Medicine. We have lower scaling Twitter for digital epidemiology of birth defects. So that all of this work, so it's not to lose hope that it's always going to take 2 years. All of this work allowed us to collapse what we did in over 1.5 years of work into 6 months. So NLP methods allowed us to cut the time it took us to find new, in this case, it was new cases, and also a better, tighter control group, about 6 months, what before had taken us 3 or 4 times as long. So we have different things, different classifiers along the way. We have medication mention classifier and extraction system. We have one that tells us whether the mention is just a mention or is it an intake mention. And then it allows us to then complete case control studies. In this case, it was birth defects. We have since done other studies with the same cohort. And the NLP methods, just to give you a taste of them, it starts even with things like generating misspellings of medications in order to collect them, not specifically for this one, but in general when we were doing pharmacovigilance. So the names of drugs can be very, very varied, and even the original name of the drug is sometimes not as popular as the misspelled version of the drug name. And so we have generating misspellings of medications. At the time we did it, I thought I was going to be able to find something that generates misspellings, but there wasn't any. It was just misspelling correction. But for collecting data from Twitter, you need to get a notion about the misspellings. Then what we have is this timeline with a bunch of tweets about all kinds of things, and we want to find mentions of medication intake. So we want to be able to distinguish the two. So this one, maybe I'm tired because I had 2 tramadol, my back is sore, so it's scoliosis. And notice, for example, things like mentions of disease and comorbidities are common in some of the tweets. Take codeine this morning. So those are examples of where intake is distinguished from just a mention. And then moving forward, we have this deep neural networks method. This was published also in 2019 to get from the timeline all the medication mentions, as I said, followed by a medication intake classifier. Challenges here, we annotated 212 timelines. This is a tremendous effort to annotate these timelines. On average, takes 2 hours. So this is 400 hours of work to get 212 timelines manually annotated. So we discovered, obviously, that it is extremely unbalanced. Only a very small fraction of tweets actually mention medications. So it's about 0.24% of tweets. 0.24. No, it's not 2.4. It's not 24%. It's less than that. So so we have we had a very big problem in this particular instance. You might wonder, like, why bother then? Like, most of these timelines won't have anything, but this 0.24 multiplies really quickly when you have a lot of data. So for 500,000 timelines, each of them having about 3,000 tweets, you can get to a really good number of mentions of medication intake. So that's the beauty of social media. You have a lot of it. And if you don't have enough, just keep collecting, you'll have more. So as long as you do it systematically, you'll have enough for studies. So in this case, we did a nested case control study. We got a group of interest, so those women that were reporting birth defects. We found a comparator group. At this time, when we published this paper in 2019, our definition of a comparator group was very lax, just because we didn't have the methods in place to do anything better than this. So it's like, yeah, don't do this at home. We're improving on it. I'll show you how. But at that time, we did that. Okay, so basically, there's no mention of a birth defect. It has some logic to it, because we were using, for example, timelines of women that report a lot. So we will expect something big, like a birth defect, to be reported. So there's some logic to it. Anyway, so from the timeline, from Twitter timeline, we get medication intake, ethnicity, age, country, and we compare. So we follow, and in the comparator group, same thing, and then we compare the two. So in general, reports of medication exposure during pregnancy were statistically significantly greater among the cases than controls. We didn't have enough cases for studying specific birth defects, but in general, we had enough to find a statistical significance in cases and controls. We're not claiming causality, so we're not saying this is the case. It might be that because there was underlying conditions, they're taking more medications and also had birth defects, not because of the drugs. So that will require some further study. There's some interesting findings in that paper. For example, how often do we find this demographics? So how often can a human can determine ethnicity or age or country of residence? And it's much higher than you will expect. It'll be interesting at the end of my talk to look at the chat. So you want to put a guess out there. How many times do you think, given a timeline, or what percentage of timelines, given the user timelines, we were able to derive the age of the user? So I won't give that answer. I will tell you, for example, that in ethnicity, we only had missing like 25% or 70%, 30% of it. So we were able to tell either the ethnicity of the country of residence. We also studied age as well. So, okay, so we did notice our selection of controls was pretty lax. So we went on and did a further study. This one was published as well. At that time, it was an archive, but the preprint. So if you have trouble getting to the AMIA papers, which is always behind a paywall, try the preprint. It has all the information there. So basically, we're looking at, on a timeline, we need to find two pieces of evidence, either in one tweet or two tweets or any number of tweets, basically, but usually it's one or two, where you have whether the baby reached term, that's 37 weeks and beyond, or and had a normal birth weight. So those two is what defines a normal pregnancy. So that's how it's defined, and obviously no birth defect present. So we have the no birth defect evident or present, and these two pieces of information. So so before or all their study only has the requirement of no birth defect mentioned. I should do the warning in social media. If it doesn't, the fact that something is not mentioned is not evidence that it doesn't exist. So that we take into account is a limitation of our studies. Getting negative information is very hard. We could always go with the negative specifically. So say, for example, not birth defects, but for vaccination. So I did not take the COVID vaccine. That will be some evidence that that person didn't take it. However, it's not even conclusive, because it could be that at the time they tweeted that, they didn't take it, or they didn't have it, or they didn't want it, but then later they changed their mind. So it's very, very difficult to say that this definitely is something that didn't happen. So we try to focus our studies on the things that happen. So the positive information. So in this case, what we can say for this controls is that the babies reach term and the babies reach normal birth weight. Sometimes we'll get a positive information for one, but not the other. Therefore, the user is not cleared as a control timeline. Sometimes we will get negative for both. Sometimes we will get different pregnancies, like 2016, one of them, but 2014 for another. and so on. So there's many reasons where even if we get positive information for each of these independently, when we put it together, it doesn't work. So that still leaves us with no user in this case. So only the last one we will count as having a term and normal Berkeley. So we are still running that study, by the way. So where we have new controls and new cases, actually. Let's skip this one. So, essence of time. So the only point that I wanted to make is scaling these studies after you develop NLP methods for them becomes much easier. So this is the nature of digital medicine. So the other point that I want to make is that you can indeed get to some of these reputable journals, I guess, with these studies when done correctly. So this is simply the next step that we should all have in mind, that we need to have the goal of using this data in such a systematic manner that it starts earning trust, and obviously then the findings from it are taken seriously. So we do have a few studies after this one, but scaling the studies is very important because, for example, at the beginning, we always have like 100 users or 120 users. We just published a study on getting indicators of having the COVID vaccine in pregnancy, during pregnancy. And we did that preliminary study with 120 users or so, trying to get the outcomes of those women that took the COVID vaccine during pregnancy and comparing to some of the other findings, and now have scaled it. So scaling up, proving that the methods are good enough for one small study, then enables us to scale it very, very quickly. So we have already scaled it. At the time of publication, we already have 3,500 users, and we have more now. And it grows very quickly. Once we polish all the NLP, then it opens the door to finding way more. So before it all happens, actually, we always start with a thorough analysis of the data itself by hand. So I use a lot of this grounded theory-based analysis, where basically we start looking at this real-world data, social media data, or forum data even, without any specific framework in mind, any preconceived structure or hypothesis. We simply start with an open question. In this case, this is a paper published in JAMA Network Open. The question that triggered this one was, okay, so what do patients discuss if they post about statins on Twitter? We were not after adverse effects. We were not after anything. We were just simply saying, okay, so if you decide to tweet about statins, what is it that you're saying? Why will you do that? So we did this, got a sample, and actually threw my most senior annotators at it. So this is not something for students to do. Grounded theory annotation requires some training in terms of what are you trying to elicit from the data. So that's why it's important. They will do it once the structure is established and you can train and you have an annotation guideline, for example. But at the beginning, when it's open, it's better to have the most senior people do it. Anyhow, this process includes then coding emergent themes with keywords and phrases, grouping the codes into concepts hierarchically, categorizing the concepts of relationships. So in this paper, for example, you will see that right off the bat, about half the data that we had was not about anything that we were going to be using. So health related or not was our first category, just to get rid of a lot of the noise. So advertisements and other things like that was eliminated that way. And then goes down the line like that. So it gives you a view of what is it that they discuss and what percentage of data falls into each category and so on. An interesting finding on this one is that people express their beliefs and attitudes. So tweets the state of belief or a personal opinion about the medication or the medication class become very, very important because it's an insight into the user's mind. And it sometimes these beliefs translate into behaviors that are not necessarily the behaviors that you want. So for example, what we uncover here that was not published before is this risk balancing approach to statins. So people that say, okay, so like the Super Bowl example, the Super Bowl is like the world final of football in Europe. So everybody tunes into that, the European Cup final, I guess. So very big sports event in the United States. So it says Super Bowl, which means it's time for the Baconator, 2 pounds of bacon and 1 pound of sausage rolled together and cooked for 2 hours into juicy goodness. I'll take 2 Lipitor this evening. So doubling up on the dose of their statin, low cholesterol lowering drug might not be the wisest thing to do, as is not the wisest thing to do, obviously, to eat unhealthy. But what we started seeing, so this is just one sample of this. So you might say, well, this is a joke. It's just one person doing these things. But we started noticing several tweets that had things like that. If they eat healthy, they don't take it. If they eat unhealthy, they take it or take a double. So really, all of those are non-adherent behaviors. So we were looking at establishing non-adherence. So this risk balancing behavior was evident then on this thing. The other thing that it signals, and I see a couple of the tweets at in this same category. I'm talking about this middle category here. Whereas they either want to replace it with exercise or healthy eating, or the other way around, where like once you're taking medications, you don't need healthy eating or exercise. So all of these are behind this non-adherent behavior of patients. So we're exploring more of that in our future research. Other tools that we develop aside from that, these studies. Okay, so we start with that annotation. The grounded theory annotation, just to close on that chapter, gives us both an initial study, like we did. It gives direction to where we should go next in our mining of this information. What is important? What can social media bring to the table? Okay. One of the common mistakes, I guess, or misconceptions is trying to make it do too much. So there's a bunch of studies saying, attempting to do, oh, we can find it earlier in social media. Those, if you read them critically, many times they claim that you can find it earlier, but the only way they found it is because they were looking for it. See what I mean? It's like, oh, a signal about, what was the latest I saw in this example? Whether social media can tell you this adverse effects of the COVID vaccine in a heart inflammation. So it was like, there's a paper published like that. But basically what they did is went and looked for keywords about indicating this inflammation of the heart, official words and so on, tried to see if there were mentions of that in conjunction with the COVID vaccine. So here is looking for tweets that have COVID vaccine and have mentions of this. Found 13 tweets, and then say, yeah, this is earlier than that, than the report, without any real evidence that this is so. Whether people were linking it before because there was news reports, so it requires a very complicated analysis of when exactly this was reported, and it actually will require this timeline analysis where you have exactly when the person got the vaccine, and then whether there were any symptoms reported and so on. So it's very, very complicated to do. It's not simple. It's certainly not a study to do with one tweet on a one tweet basis. So anyhow, we always take and we always encourage what we call the pipeline approach, where social media data needs to be processed from beginning to end. How you find it out there and what is your information retrieval strategy, through all the steps of classification. If you're extracting concepts, then name entity recognition, and then which normalized name that concept or that entity is mapped to will be our next step. So the output of a system should culminate in normalized names that can help you do the analysis of the data in a sound way. So we have the ADE Miner is a state-of-the-art pipeline approach at gathering adverse drug events reports from social media. We are now equipped, and this is 2021, Our first paper on this appeared, I think it was 2012. It was called ADR minor, so adverse drug reaction minor, in appearing JAMA a few years back. I'm trying to think if it was 2012 or 2014, something like that. So it has taken many, many years to complete the whole thing. We are equipped now with our collection. We've been collecting tweets on medications ever since then. So we have a large, I believe is the largest collections of tweets about medications that exists. We have them all. The next step in this case will be the signal to noise analysis of whether we can derive signals of ADEs with the state-of-the-art NLP from social media. There was other studies published that I will say are not using the optimal NLP methods in the middle. So WebRadar in Europe is the biggest study in this sense. They did an excellent job at setting up the input data from different sources and at analyzing the output. My only concern is in the middle with the NLP engine that they use. Definitely could not extract or normalize dimensions as we can now. So that will be upcoming. We also have this system, symptom extraction in English using deep learning from social media pharmacovigilance. This was published as an archive about a year ago. We are about to release it again, submitting to a journal. So version 2 of this paper will go to archive before we submit to a journal again, because we changed some stuff in the approach. So an updated version of this will be there. Very, very important for many studies that you can get all symptoms and not just adverse drug events. So up to now, most of the work in social media mining of this kind has been around adverse drug events and adverse drug reactions. A lot of it has been done on that. But trying to get symptoms that are not tied to mention of drugs opens up the possibility of studying many other things in social media, particularly, for example, for COVID and long COVID. We needed some system that could get me symptoms that are not tied to reports of drug intake. So in this example on the slide, you see that this is actually aimed still to the ADR realm, but we have opened that up so that now it is a generic symptom extraction system. And we will be making it public soon. All right, so trying to wrap up. I'm not exactly sure about the time that I should end, but if I don't have any more time, I could stop, but otherwise I have about 5 more minutes for organizers, if they can give me like a little.
Fine, fine. You can continue for 5 more minutes. It's
all right, thank you. So, so this is directions of research, future research. So detecting medication non-adherence in Twitter, as I said, that is a fruit of the study that we did with statins. Like this is something that social media can bring to the table. Why people are not adherent to their medication is a very important area that is very difficult to study because, for example, this kind of behavior, like the one I was mentioning, about taking double the statins when they eat badly. When the doctor asks in the office, it's like, oh, did you take your medication? And they will say yes, because they took it kind of in their mind. Good enough. So it's very hard to do, even when they run studies on this. So the doctor will think, okay, they say they took it, they seem to be refilling the prescription, which is one of the first signs that they are taking it, and it's not working. Well, let's either, and then they make a decision, say, oh, let's add to it. Let's add to the dose. And really the patient was non-adherent, or either because the behavior was non-adherent or because the drug intake was non-adherent. Anyhow, so this is the direction where we're going. When they change medications, so we redefine the way we look at the problem, because adherence is a very specific thing where they say it is done, a patient is non-adherent when they change medications without their doctor consent. Establishing the part about without their doctor's consent is almost impossible in social media. Sometimes it is, for the reasons I mentioned before, right? They will say that they changed, but then don't tell you if they told their doctors or not. Or even if they say, as I said, it might be that at the time the doctor didn't know, but then later they knew. So this little business of adherence is very difficult. We did establish, though, medication change. That is easier because that's language. So we did, when they changed medications, they would switch medications. We were able to get the tweets that mentioned that. And then we analyze it by hand for any evidence of non-adherence and then the reasons given for non-adherence. So in a small study that we ran on this, we analyzed 3,000 tweets that mention a medication change. Not tweets, this was actually from WebMD. We did found that the reasons given most of the time was because of adverse events experience. So 72%, misuse was the next category. Access to the medication issues was 48%. And I'm sorry, this is not percent, this is counts. So 72 out of the tweets that we analyzed, 375 tweets, 87% stated the reasons, and the rest didn't. They didn't give a reason. They just said they switched medications. And amongst the reasons we found adverse events, misuse, access issues, belief, unintentional and non-adherence, parents' decision, efficacy, stigma, and other. So we do have a way to do this, and we've opened up that. We have a shared task challenge coming up. Those of you doing NLP, we're running social media mining for health, the 7th edition of it in 2022 at Calling. And so this is one of the tasks, that detecting medication change in Twitter. Anyhow, just to conclude, why is it that we cannot see, or we don't see more? So all of this that I've done in social media, a lot of it is going to be migrating to, and it's already in the process of being used in electronic health records. One of the main problems that we found in electronic health records, despite it being the data that has been used for clinical research in NLP actually for many, many years, is actually not, most people don't actually use NLP for their studies in electronic health records. It was very surprising to me. I was doing a study last year, so I'll tell you a little bit about it. So tools, NLP tools for extractions are generally not available for electronic health records. So this is a paper, it's a systematic review published in 2019 by the editor of JMIA, the senior author of this paper. So I will hope that she knows what she's doing. So I trust that she knows what she's doing, and this was done well. It says here that that a lot of the symptom extraction, that is like the reason I was running this study, is actually not done in general. Most people do symptoms on the way to some other goal. So if they're studying COVID, they will study COVID symptoms. Cancer, they will study the medication adverse events of cancer treatment, and so on. So it was always done on the way to something else. And so the end goal was never extracting symptoms from electronic health records. So at this point, there's no generally applicable engine for symptom extraction in electronic health records. So that's a challenge. The tools are never, this was switch around, sorry about that. This was my last slide about social media and COVID. So I'll just mention this, like we did some work on social media and COVID. We have the largest collection of them, and we've been publishing papers. So this doesn't require a lot of bandwidth at this point. This is the point I was trying to make. Electronic health records and its challenge. So it's a data revolution. There's a lot of data in electronic health records. Its wide adoption around the world has opened the door to studies at a scale that has never been seen before. There's clinical and genomic data from a broad and diverse patients in many, many different hospitals. However, at the individual study level, 70 to 80% of the data they will have available is never used. This is because most published research uses only the structured portion of the record. So data in discrete fields. I didn't know how many. It's very difficult to calculate. So I'll give you my estimate. This is my estimate of what percentage of the studies done on EHR data actually use the unstructured portion. So we discovered that that all of this abundant free text in admissions, progress and discharge notes and radiology and pathology reports is very rarely used. in these generic studies run on EHRs. My calculation is that less than 1% of the studies published use the unstructured portion of the record. We were running a search. It was on bias on gender-specific outcomes found from EHR data. So anyhow, from 67,000 papers that matched the study-related keywords. So basically, just to scope it down, these were studies that found gender-specific outcomes. So it's a paper that needs to appear actually. So out of these 67,000 papers that match or study-related keywords, only 469 match the keywords indicating machine learning, NLP methods. So anything that we can use as a proxy to know that they use the unstructured portion. Deriving who used the unstructured portion of the notes is very, very hard, almost impossible. So we use a proxy. We use any keywords that indicate an advanced method of analysis, which is sort of required if you're using unstructured portion of the record at a large scale. So large scale, unstructured portion, you have to use some of these advanced methods. So 469 of 67,000 papers in March. So that's like close to 0.5%. So I'll give it less than. This is the paper I was talking about. It's to appear in the annual review of biomedical data science this year. I didn't archive this paper, so we'll have to wait until it comes out. I think I can still archive, but I'm not sure. I'll check. Anyway, it calls out some best practice on big data analytics to address sex-specific biases in our understanding of the reason for disease. So that's to come up. I won't dwell on it. Resources available. My center has made available many of these resources, annotated corpora through the SMM4H series of workshops, running since 2016 every year. So we still have those available, data sets available. Semi-Val 2019 task 12, BioCreative 7 task 3. So we organize shared tasks on a regular basis. And we also have web services. Some of them are at different stages of release. Most of the ones that you see here are available and you can use them, and we welcome any use of all of this data. All right, and with that, I conclude. I thank you for listening. And these are some of the contact information. My Twitter, social media feed is a very, very simple way to reach me. We have the site of our HLP Center, and I really, really appreciate all the attention, and on behalf of my team, thank you so much.
Enlightening presentation. And I have a question, an important question, because we are used to clinical data from clinical trials. So we are focused on data quality. And for us, it's quite difficult to foresee the impact of data quality on the management of real-world data and social data. So it's very difficult for us to trust the quality of some kind of real-world data. And I would like to know your feelings, your thoughts about that.
Yes, it is indeed difficult to trust the quality because you need to define the quality first. And every study of any kind with any sort of data will have limitations. So the only thing that we need to acknowledge is these limitations in order to make the study possible, right? So you do your conclusions and your analysis within the realm or within the bounds of the limitations of your study. So surveys have limitations and biases. And actually, people that do surveys for a living, I work with Sue Golder from the University of York. She worked with the Cochrane Group, and she has been running surveys pretty much her entire professional life. And she's the one that most opposes the use of surveys as the main gold standard, because she says that really they are very, very biased. That you get the same people to answer the surveys all the time. and that you don't reach that. They are expensive, and you just like run them once, and it's very difficult to run them again. Anyway, so it has all kinds of limitations. Any data will have. So the only thing that we have to acknowledge is that yes, social media data will have limitations. That doesn't mean you dismiss it. That means that you analyze the process through which the data got to this analysis, through the pipeline and to the analysis step. And each of those steps to get you the data. So if you're doing an analysis or a use of the data for, say, reports of adverse events or drugs, you cannot dismiss it. You cannot say, which I think I've been a victim of in a way in reviews for my proposals and so on. It's like, oh, it's all trash. Well, it's not all trash. It's there. People are suffering through this and they express it. And so if you take care of how you're collecting this and you have enough of it, then it is evidence of something, right? It might not be conclusive evidence. It might be just enough to send you searching and doing a more focused study, but it will certainly save you money in directing it. It will broaden the scope of your study, for example. So instead of being limited to the people you can reach physically, now you can get data from around the UK or around Europe or around the US using a sound collection practices, analysis practices, validation practices. So for any of the methods that we use, we have validation. And I tell you, yeah, my system at this point is, I don't know, 89%. I give you precision and recall. So yes, we're missing a part of it because I mean, I have, I don't know, 76% recall. So I will be missing some. But the stuff I find is, say, 92% precise. So I give you these validation parameters and we operate within those. And then obviously in the analysis and statistical methods, we can do that. We can apply data missingness approaches, just as in regular studies. So what do we do when data is missing? Well, the same thing you do when data is missing from your surveys, because people don't ask every single question, right? I mean, don't answer every single question.
It's clear. We need to get the best out of it. Yeah.
All right.
Thank you. We are running out of time, but I have the pleasure to make a final question to Rachael, because during her presentation on causal machine learning, she told us that there is potential for targeted learning in applications in combination with natural language processing, derived covariates, and also with data from electronic health records. And so we think that there is a connection with the kind of data that you use and what Rachael mentioned. So it would be nice to have her opinion or a clarification on that. Rachael, are you here?
Yeah, I think that, I guess I'm a little bit confused about the question. You can use covariates that are derived from EHR data or natural language processing.
Yeah. Yes, I just try to explain. Graciela talked a lot about deep learning when analyzing this data. And I think that I read on a slide that there is also potential for maybe super learner for applications on data sets combining natural language processing derived covariates with electronic health records data. So I just wanted a clarification on that. Is there a struggle between deep learning and super learner, or I don't know? Which is the meaning of that set.
So you can use deep learning to derive these covariates, as Graciela was mentioning. If there were other methods that were being considered to derive these covariates, or different ways to tune a deep learning model, you could consider all of these variations in the superlearner. This would provide a way to use cross-validation to select the best model.
And also we use active learning as well. We've deployed active learning a lot in trying to get the best input from the limited resource, which are annotators. So, so that is one thing I didn't mention as well, that it will help.
And so which is in your opinion, which is the most promising approach? Also pipeline, because there are a lot of things to do.
Pipeline.
We have to do pre-processing and whatever. And just a quick question, which is the most promising in your opinion, the most promising approach? Graciela, and then Rachael, if you have an opinion.
We've had really great results with deep learning and BERT-based classifiers. We have incorporated the specific BERTs, like there's a social media or a Twitter BERT, and then there's a clinical BERT and so on. We do have seen almost invariably that those classifiers outperform the others in most instances. We still find on occasion some, we have to like do some cleanup up front of the data. So for example, just to illustrate that they are not perfect, these deep learning based classifiers and BERT classifiers are not perfect. Even though performance, for example, for classifier on, which was it? I think it was some of the COVID discussion. Anyway, it was outperforming the others. But when we did error analysis, most of the errors of the classifier were still in the same category that we were trying to address. So we're trying to address quotes. When people do citations of things on the newspaper or that somebody else is saying. So all of these references to reported speech, where so we did a whole thing to try to detect reported speech with regular expressions and so on. And I mean, it didn't end up helping the other classifiers. It didn't end up on average helping the BERT classifier, but it was still present. The most sources of error for the classifier were reported speech. So there's still room to do a lot of fine tuning upfront, a lot of fine tuning in analysis, for example, to try to find some of these things. But yeah, in general, yeah, I mean, deep learning and all of these advanced methods are the most promising, combined with things that will help with data in extreme imbalance, for example, is a major problem because that makes any classifier fall flat. So for drug mention, for example, we went from being very happy with an 82% or so F measure, and then we let it loose on a timeline where the number of positive instances was like less than 3.3%, and it just fell flat. We went down to 3%. So the extreme imbalance is another one of the challenges that we have to address.
Yeah, yes. We know we dealt a bit with it with Corrado about class imbalance in, when using different classifiers. Well, I thank you so much, and I'm really glad to chair this nice session, and thank you for coming, thank you for being here with us, and that's all for today. And for the audience, I say join us tomorrow for the third session of this winter school. Thank you, Corrado. Thank you, Rachael. Thank you, Andrea. And it's been truly a pleasure for me to be here with you and with all the other attendees and the organizing committee. Thank you very much. Bye-bye.
Thank you.
Thank you.